Good evening, everybody. So, we'll continuing with the types of bonding, what is present in complexes. So, at this particular point, when people were talking about this bonding, so quantum mechanics was not developed at that time, and the only idea was there that electron pair can be utilized for sharing. So, the historical perspective for this bonding nature, if we consider in this second part of bonding in complexes, we will see that during 1893, when Alfred Werner proposed this sort of complexes, and at that time the bonding idea between two atoms was not so clear, and he proposed that a particular type of metal ion can bind to so many ligand systems such as water molecule, ammonia molecule or ethylene diamine molecule, and give some important characteristics for those species which we can derive when the metal is bound to the ligand system. And at that particular point, when the valence bond theory was gained ground, and we see that a covalent bond can be formed from sharing of the electron pair between the two atoms. And following this time frame, that means around 1893 or so, after that this theory, the valence bond theory, gained ground, and we were able to explain some of the geometrical features, the compositions and little bit of the structural aspects of these metal complexes. But it could not explain so many other things like the color, the magnetic property and the reactivity of some of these complexes we could not explain using the valence bond theory. So, slowly the crystal field theory, which was originally proposed for the crystals, was gained ground, and people were utilizing the crystal field theory for explaining the bonding nature, the type of bonds in all these metal complexes. So, in this particular class and the following one also, we will focus our attention on this particular theory, that how crystal field theory can explain so many important properties and aspects of the metal complexes. Then we will just follow that crystal field theory with the modification, the ligand field theory, and finally to the different molecular orbitals to the entire molecule, that means the molecular orbital theory. So, Alfred Werner, who just proposed the concept of this complex formation, and two types of bonding he proposes at that particular time, and immediately after say 20 years he got the Nobel Prize for this idea of getting these complex species in solution as well as in the solid state. And he proposed two things, that one is the primary valence and the second is the secondary valence. And whenever we are talking about the valence bond theory, we should know about, we should have good idea about the valence structure of the species. So, the primary valence, which basically corresponds to the oxidation state, so it is nothing with relation to the corresponding coordinate bond, it is simply like that of the presence of 3 chloride ions around aluminum center in aluminum chloride, or 2 chloride ions around barium in barium chloride. But the most important thing or most interesting thing is this secondary valence. So, this secondary valence can be correlated to the coordination number. So, this secondary valence, when it is fulfilled by the metal center, we find that certain metal centers can have a coordination number of 2, and in some other cases the coordination number can go to 3 or can go to 6. So, depending upon the number of coordination, we can have the corresponding geometry also, and the valence structure of the metal center can give some proposition what we have seen on our previous class, that the hybridization scheme, which was originally proposed by Linus Pauling, that the hybridization scheme can be applied to these complexes to explain to some extent the geometry and the corresponding property, at least the corresponding magnetism of these complexes, which were very much important because most of these compounds first studied by Alfred Werner, who is on chromium, is on cobalt. That means the first transition series elements, which were nearly all of them are paramagnetic. But if we find that during the complex formation the paramagnetism is lost, that means the compound becomes from a paramagnetic site to a diamagnetic one, that means the coordination is doing something very great to this particular complex formation. That particular information and that knowledge is very much helpful when we consider some of these biological molecules like myoglobin and hemoglobin. The magnetic properties of these biological centers are very much useful to identify the corresponding oxygenation reaction, because oxygen molecule itself is also paramagnetic. So, when the center, which we can consider as a metal complex, is also binding to another center which is also paramagnetic. So, what should be the overall property of the metal bound species, whether that would be diamagnetic or paramagnetic, that gives us some idea from the studies on these particular type of complexes. So, we have seen that the valence bond theory were unable to explain so many important things. It cannot clearly account the color of the complexes, whether the solution color of the complexes would be green, would be blue or would be violet. So, for this particular bonding, that means D2sp3 or sp3d2 type of hybridization for octahedral complexes around the nickel 2 plus ion cannot nicely explain the color, or to be specific the color change, how the color change is taking place as we change the ligand center around the metal ion. It might predict the magnetism wrongly. That means it cannot say nicely that what should be the precise magnetic moment of that particular complex species, and which is very much important for a large molecule like a large biomolecule like myoglobin or hemoglobin to know the magnetism nicely. Then only we can have some idea about the interaction of the metal center with some other paramagnetic species like dioxygen. It also cannot account for the spectrochemical series that we will see afterward, that in a spectrochemical series we can arrange the ligands according to their strength, and that strength will change the corresponding color of these complexes. If we can have some 5 or 10 ligands in our hand and all of them are interacting with a particular metal center, say nickel 2 plus or copper 2 plus, then we find that depending upon the binding or the complexation of all these ligands, we find that there are changes in the corresponding color. So, how we arrange those ligands in a particular series, and that series will be called as the corresponding spectrochemical series. So, valence bond theory cannot explain nicely the corresponding color of these complexes, and it cannot arrange these corresponding ligands. So, we just proceed towards the crystal field theory. So, crystal field theory gained ground from the assumption that a particular metal complex is forming, say iron 3 plus is forming the metal complex with thiocyanate anion. So, iron 3 plus, which is a hard metal center. So, according to hard and soft acid base theory, it is the nitrogen end of this thiocyanate anion will bind to the ferric ion, and the interaction is that this is a positively charged species and this is also a negatively charged species. So, the interaction between the positive center and the negative center can be considered nicely by assuming that the one particular center is basically from the crystal lattice, and this interaction is purely ionic in nature. So, this particular assumption is very much true when we consider the interaction between Na plus and Cl minus. So, Hans Bethe proposed this idea that if we just simply consider that this particular metal center, that means the ferric ion, equivalent to that of the sodium plus in sodium chloride lattice, and Cl minus is our ligand like that of our thiocyanate anion. So, the ligands what we can have in this particular theory. So, we have the CFT, the crystal field theory, which gained ground slowly after the identification and the establishment of the metal complexes. So, we have these ligands. This is also the corresponding ligand which is binding to the iron center, and this is in the sodium chloride center. So, the ligands binding to the metal center through the atom, that means either through nitrogen or through Cl minus. So, they can be considered as point charges. Abbreviated as PT, point charges, or point dipoles. So, we are considering as them as point charges or point dipoles. So, thus that the charge is centered basically at the center of gravity of the species. So, point charges and point dipoles, if we have water molecule also, we will have the delta minus dipole charges. So, this particular charge, the negative charge which is centered on oxygen, can be considered as a corresponding point dipole, and it does not consider any overlap between ligand and metal orbitals, which we proposed basically in case of valence bond theory. But this particular case we are not considering this thing, because we are considering only crystal within the crystal lattice, the cation anion interactions which are purely ionic in nature. So, these overlaps basically gives rise to some informations what we can get from this particular theory, that basically the visible spectrum, the color, say from 400 to 800 nanometer, starting from violet to red. So, if we can find that the 3D elements, the transition series elements in the first series or the second series or the third series, when they are in solution interacting with different point charges or dipoles to give the corresponding complex species, even if that particular metal salt is dissolved in water, it is interacting with the aqua molecules, or through deprotonation it is also interacting with the hydroxide ion or oxide ion. So, it basically gives the color. So, it can also little bit explain the origin of the color in the solid state also, say some precious gem material or the minerals which is colorful, where due to the presence of the transition metal ion. So, transition metal ion in the solid state also in some crystalline environment can also be considered as the interaction, such as the corresponding crystal field theory, which can little bit explain the relationship between color and the complex metal ion. So, what is the complex metal ion, whether it is in the solution or in the solid state, we can get some idea if we consider that the corresponding metal ions in the D levels are responsible for the transitions to give a particular metal complex green or light green to blue to violet. And we will be considering slowly all the different orbitals, corresponding orbitals we can have. Sorry, this is the corresponding octahedral geometry where we can have this that octahedral geometry where we can have the central metal ion and the three Cartesian axes x, y and z, and this is basically giving rise to the corresponding octahedral crystal field. But the basic assumption behind that, all the 5 d orbitals, these are the 5 d orbitals which are placed inside an octahedral crystal field. So, how the d orbitals will behave in this particular crystal field. So, this particular theory is therefore a model. So, we will by using this particular theory as a model to explain some of the known facts or some of these experimental facts. So, this is basically a theoretical justification for all these metal complexes about their bonding pattern. So, it can explain whether some complexes are high spin and some are low spin. So, high spin and low spin complexes, what we will get, that if we have this particular iron center what is there and is binding to say 6 thiocyanate anions. So, NCS and overall charge is 3 minus. So, this basically gives us, because we all know the free ion magnetic moment, that means how many unpaired electrons it has. So, after complexation we can have two situations. One, we have a paramagnetic situation, or another one is the diamagnetic or close to diamagnetic one. So, in one case we will see that the magnetic moment is high, that means it has high spin values, that means the number of unpaired electrons would be more. In another case, the situation will give us a low spin configuration where some of these are paired up. So, the number of unpaired electrons available would be less compared to this high spin molecule. So, we get another low spin type of molecule. So, two types of molecules we can have due to complexation. So, these are the results for complexation reaction. So, we can have the high spin and low spin complexes for that particular purpose, and it also views the bonding in complexes as a result of electrostatic interactions. So, we are talking about the ionic interactions. So, the interaction between the metal center and the ligand is purely electrostatic in nature, and it considers the effect of ligand charges on energies of the metal ion d orbitals. How the ligand charge, which we are considering as point charges, how they are interacting with the metal d orbitals, and it is changing the corresponding energetics of the metal d orbitals. Otherwise, in absence of that particular crystal field of the metal complex, all the 5 d orbitals are degenerate. So, the degeneracy will be lifted when we put the ligands in a particular coordination environment, and the number of ligands around the metal center are also specific and important. So, when we consider that only electrostatic interactions are operating, we should not consider any kind of covalent interaction. Thus, crystal field theory uses no covalent bonds. That is why valence bond theory has been discarded, because where we have considered that the hybridized orbitals are overlapping with the ligand orbitals. So far the development of crystal field theory above the valence bond theory gained ground only by considering that the interactions between the metal and the ligand, and the interactions what we all know now, that the interaction between the iron center in hemoglobin with that of the dioxygen molecule when we use the dioxygen molecule for our respiration can also be considered as electrostatic in nature, but that is not purely true fact, because afterwards when we modify the crystal field theory by ligand field theory or purely the molecular orbital theory, we will see that slowly that the pure electrostatic interaction is not the only fact, but we can have some amount of covalent interactions at the same time. So, what model we can use for this particular type of crystal field theory is that a purely ionic model. Therefore, we are discarding any kind of covalent interaction, whether some percentage of covalent interaction can be available from there, but we are not considering that particular interaction. The ligands are considered as point charge, that already we have told you. It predicts the pattern of splitting of d orbitals, which is the important fact. So, the number 3, the point number 3 is the most useful one. How we consider the splitting of the d orbitals, that in the two types of d orbitals we can have in a particular coordination geometry, and one d orbital is available for giving the electron for the transition to the other d level, and we will get the dd transition, and which can be rationalized for the corresponding color of the complexes. So, this particular occupancy, the differential occupancy of the d orbitals, which are non-degenerate now in presence of the crystal field, can be rationalized for the spectroscopic signatures, what type of absorption spectra we get, and the magnetic properties, whether the compound is paramagnetic, whether it is diamagnetic, or it can have some intermediate magnetic moment, or it can have some dependence with that of the temperature. That means, the temperature dependence of the magnetism can also be very nicely explained if we just consider that there is some equilibrium between these two states. That means, the high spin state and the low spin state has some temperature dependent equilibrium. Then we will find that due to the variation in the temperature, we can have one particular geometry than the other. So, what we have seen that we know the corresponding field, that means the octahedral crystal field, and this octahedral crystal field can have 6 ligands around the 3 axes, 3 Cartesian axes x, y and z. And if we just simply consider that particular metal ion is there and the corresponding orbitals under interaction with the point charges of the ligand. So, what will happen if we also consider not only the d orbitals, but the s and p orbitals. So, we can have s orbitals, we can have p orbitals. So, s orbitals we all know is spherically symmetric in shape, which has electron density around all the 3 axes. So, when we have the s orbital in octahedral crystal field, we put this in crystal field. Since the ligands are there in all 3 Cartesian axes, these are the point charges which will interact with the metal center at the center of the geometry. So, when the s orbital is facing all the 6 ligands symmetrically from all the 3 Cartesian axes, we do not get any kind of splitting. So, it will not give any splitting for their energies. So, if we have more than 2 s orbitals, we do not expect any kind of splitting due to the crystal field available from the ligands in a particular coordination geometry, which is octahedral. Then what happens for the p orbitals? So, when we have p orbitals, they are 3 in number, px, py and pz, and if we put the same octahedral crystal field, we will find that if this is the z direction, this is the x direction and this is the y direction, then the px and py will face the ligands as well as the ligand will also face the z direction. So, all three were there before interaction, that means the free ion p orbitals and the complex p orbitals. Only the energy can be increased little bit, but there is also no splitting. So, if we have some amount of preferential coordination through some axis, then only we can have some kind of splitting from one particular direction. So, now if we can put the p orbitals in xy plane, that means the square planar one. So, if we just put that in the square planar one, then we will find that this particular thing will change differently. That means, now the crystal field is square planar and the square plane is such that we have the 4 ligands in a particular square plane along the x and y axis. So, since these two ligands are in x and y direction, so px and py will face only the point charges, the ligands. So, they will face them and pz will not face any such interaction, because along this we do not have any ligand. So, the pz orbital will be stabilized and px and py will go up energetically. So, there will be splitting in square planar environment. So, p orbitals can also give rise to splitting in a geometry which is different from the octahedral geometry and can have some preference for the interaction with the ligand centers. So, now we will just see how the 5 d orbitals of different shapes can be placed within a octahedral field. That means, if we have the octahedral field, we have the 6 ligands along x, y and z direction. How all these 5 d orbitals can interact with the tetrahedral complex having a TD geometry, where only 4 directions will be occupied by the ligands, and then with the square planar one, which has a symmetry level of D4H. So, just now we have seen that in square planar environment, since the pz orbitals is perpendicular to the xy plane, the coordination plane, the pz orbital will not interact with the ligand centers, the ligand point charges. So, that is why the pz orbital is only stabilized, px and py will have some higher energy and there will be splitting within the all p levels. So, similarly, how the 5 d orbitals will split in a particular square planar complex also we will see, and we will see other geometries as well, because we have discussed so many coordination numbers. We can have the 5 coordinated square pyramidal geometry, we can have the 5 coordinate trigonal bipyramidal geometry. So, how the 5 d orbital ordering we can get and how we can predict the pattern of splitting of d orbitals. So, this is the most important point for the crystal field model, is how we can predict the different pattern of splittings of d orbitals in different coordination geometries. So, if we look now the different d orbitals along the axis. So, this is one particular set, the dxy, dxz and dyz, and this is dx square minus y square and dz square. So, this is one particular set because dxy, dxz and dyz these three orbitals have, all of them have 4 lobes. So, the shape of the orbitals are of same type. So, the 4 lobes which are available are centered and concentrated between the coordinate axis. So, what we are talking? We are talking that the ligands will approach along the coordinate axis, but this set of orbitals will be concentrated between the coordinate axis. That means, we have the coordinate axis like this and our orbitals will be in between, and our ligands will be from this side and from this side. So, they will not face directly towards the ligands. So, they will away from the ligand. So, there are interactions, but the interaction, the magnitude of the interactions, the point charge interactions between the metal center and the ligand center, ligand as the point negative charge or the point dipole would be less compared to the other orbitals if they are facing directly to the ligand centers. So, these basically will give us some idea that when we have the dxy, dxz and dyz, so we see that the lobes are concentrated between the x and y axis. The 4 lobes are in between the 2 axes x and y. Similarly, yz is also between y and z, and xz and yz is also between y and z. So, between these 2 Cartesian axes, so this particular orbital is a planar nature occupying the particular plane where it is designated as xy. If it is designated as dxy, it will be lying only in the dxy plane, and along the z direction we have no electron density. In a similar fashion, we will see that the p orbitals, the way they have been splitted in a square planar environment, similarly the interaction for the square planar geometry for the xy plane would be different compared to the other orbitals that we will see. So, these are one particular set of orbitals. The other set is dx square minus y square, where the lobes are directly along the Cartesian axis. In case of dx square minus y square, it is along the x axis and along the y axis, because this dxy is in between x and y, and dx square minus y square will be along x and y axis, and dz square is nothing but we have the lobe along the z axis and a circular lobe along the xy plane. Basically, it can be considered as dz square x square minus y square, minus x square minus y square. That means, we have the concentric lobe along the x axis and along the y axis. So, these 5 orbitals, when we place nicely within the octahedral field, this is the octahedral field. So, we will place that all 5 orbitals will be placed along the octahedral field, and this is now is the combination of dz square minus dx square and dz square minus dy square. So, dz square is nothing but dz square minus dx square minus dy square. So, it is can be written as d2z square minus x square minus y square. So, which we abbreviate simply as dz square. So, we can have the octahedral field. First, we will start from the octahedral field, not with that of our linear field like a coordination number of 2 or a coordination number 3 or 4, but we can simply go for the simplest example where we can have the octahedral field and we have the 6 ligands along the 6 directions along the Cartesian axis x, y and z. So, just now what we have seen that dxy, dxz and dyz have 4 lobes concentrated between the coordinate axis. Similarly, what we have seen that dx square minus y square and dz square, these two orbitals are of different type. Not like that of dxy, dxz and dyz. So, this dx square minus y square have lobes along xy axis, along x and y axis, and dz square has 2 lobes along z axis and a concentric one in xy plane. So, thus we can have some very good idea about how the lobes are placed for the 5 d orbitals. So, if all of them are placed in a octahedral field. So, now we can visualize that where we have the x, where we have the y and where we have the z, and how the 5 types of orbitals, we can now have the 5 different types of orbitals, how they will interact with the ligand system and whether the overall energy of the 5 d orbitals will be raised or not, that we will see if we just simply monitor the corresponding interaction in this particular field. So, we bring the ligands around a crystal field which is octahedral in nature. So, if we have the dxy orbital and the 5 these small green points are the ligands. So, the 5 ligands, 6 ligands along x, y and z are there. So, these 4 ligands in the xy plane are close to these orbitals and they are interacting with the ligand point charges or dipoles in a particular manner. Similarly, the other 2 also, the dxz and yz. So, they are not directly facing the corresponding ligand point charges. You see here, this is the dyz, the lobes are between y and z axis, but the ligands are along the y and along the z. So, this is quite away from the lobe. Similarly, this ligand is also quite away from the lobe. So, since they are not headed away, head to head interaction, the head to head electrostatic interactions we are not getting for this type of interaction for the metal and the ligand. But this particular one, that means the dx square minus y square, we now see that the 4 lobes along the x and y axis are facing directly for the 4 ligands. So, they will interact differently compared to this 3 set. Similarly, dz square also along the z axis we have the 2 ligands. this is one and this is another one, and they are directly facing the lobe, because this concentric lobe in the xy plane is a very small one and which is not interacting much with the ligands present in the x and y direction. So, we put all the 5 ligands in a particular octahedral crystal field. So, we find the repulsions. The d electron to ligand electron repulsions affect the d orbital energy level. So, these d electrons which are present there, they will now interact differently with the different ligands. So, these we can have from the book of McMurray and Fay 4th edition. So, if we have the 3d orbitals which are 5 in number, and the way we have placed the crystal field over the s orbitals and over the p orbitals, we will see that the same octahedral crystal field, if we put on the 3 d orbitals, so there will be different types of interactions, and the d orbitals will no longer remain degenerate, will no longer remain degenerate. So, we will have the corresponding splitting. So, there will be difference in energy for these 5 orbitals. So, one set will face different interaction compared to the other set. So, if we have thus the free ion orbitals, the free ion orbitals are 5 in number, say if it is Fe3 plus, we have the 5 d orbitals available for Fe3 plus. Then we put the ligand, if they are octahedral, we put 6L, such as we have seen that we can have 6 thiocyanate anions, and we have a characteristic blood red coloration for that. So, we have, when the 6 ligands are bringing together, so overall energy of the 5 orbitals will be raised. So, overall energy is raised, and the situation we expect before, immediately before the splitting. So, we do not have splitting at this particular point, but the overall energy will be raised over there, and after that we have the splitting, and 2 sets of orbitals, the dxy, dxz and yz set of orbitals, they are away from the ligands. So, they will be lower in energy, and the 2 other, the dx square minus y square and dz square, they are face to face with the 6 ligands. So, these 2 orbitals are face to face with the ligands. Face to face with the 6 ligands. So, they will be raised in energy. That is why we are here. And the other, they do not go for any interaction directly like this, they will be lowered in energy. Lowered in energy. So, we have two sets of orbitals, one will be lower in energy and another will be higher in energy. So, we have the splitting. So, here we have the splitting. So, crystal field theory thus gives us the splitting, and this particular center which we get here after the raise in energy, when 6 ligands are brought together around the metal center, such as 6 thiocyanate anions around the ferric ion. So, it has a center of energy, and that energy is known as the corresponding barycenter. Which is nothing but the center of gravity of the energy. Of the energy of 5 d orbitals. So, with respect to that, we have the splitting. So, we have one magnitude of splitting, this we can consider as x, and another is y. So, if now we have the total splitting, that means we have two levels in one set of orbitals, in another case we have another set of orbitals, and this is the barycenter, and this we are considering as the amount of splitting is y, and this is the amount of splitting is x. So, this is now well known to us. So, now we can just simply consider this, what is the effect of the crystal field. So, the effect, what we are now looking, effect of the crystal field. Effect of the crystal field is therefore the splitting in two groups. So, two groups of orbitals will be there, and we just consider this as the crystal field splitting is delta O for octahedron, or we can consider as 10 dqO, and these O, the level for O are for octahedral geometry. So, this O and this O are octahedral geometry. So, this particular delta 0 or delta O can be defined as the corresponding crystal field splitting and is a measure of the crystal field strength. It is therefore a typical measure. How we can measure? So, if the delta O is bigger, we have bigger crystal field strength. If it is smaller, we have a smaller crystal field strength, or we can consider it as a crystal field splitting parameter. And we just simply measure by measuring this delta O, that we can measure the corresponding strength. So, if we just measure the corresponding delta O, we will be able to measure the corresponding crystal field strength. So, that is our choice now, that how we can measure the corresponding crystal field strength by looking at the different splitting of these orbitals, where we find that an octahedral array of negative charges around the metal ion we have, the ligand and the orbitals lie on the same axis as negative charges. Therefore, there is a large unfavorable interaction between the ligand and these orbitals. So, we should have an unfavorable interaction between the ligand and these orbitals. So, the corresponding electrons on the different orbitals will stay away. The dxy, dyz and dxz orbitals bisect the negative charges that we have seen nicely. Therefore, there is a smaller repulsion between the ligand and these orbitals, and these orbitals therefore form the degenerate low energy set of energy levels. So, they are lower in energy, but they are all again degenerate, and degenerate low energy set of orbitals in an octahedral crystal field is therefore comprising of dxy, dyz and dxz orbitals. So, now is a clear view from all the orbitals within the crystal field, that means the crystal field is octahedral field. So, how the octahedral field, then where the ligands are and how they are going to interact with the different orbitals can be seen. So, the same thing we can have also if we can just simply draw the other coordination geometry. So, best thing to do is that we have the coordination geometry, whether it is a trigonal bipyramidal geometry or square pyramidal geometry, we will try to put that geometry on and above all these ligand related centers where we have the metal orbitals are available. So, metal orbitals are there and we put the ligands and then the ligands around the corners of a regular geometry, and then we can visualize about the amount of interaction between the ligand point charges with the different d orbitals. If the interaction is more, the energy of those orbitals will go up, and if the interaction is less, the energy of those d orbitals will go down and they will remain as the lower energy level. So, what we get therefore in the octahedral field, we have all these ligands in all these different points. So, this is giving us one particular set and this is giving us another set. So, from some spectroscopic terminology, we label this as the doublet state because it has two orbitals only. So, it will be labeled as the EG set, and the other three, those who are lower in energy, can be considered as the T2G set. So, T2G set will have the orbitals dyz, dxz and dxy. They are degenerate and we have a triplet state. That is why T stands for triplet and E stands for doublet, and within these they are now degenerate. So, the electron can move from this to the other level very nicely without being pushed for the corresponding barrier, which is now our crystal field barrier for the transition from the lower energy to the higher energy state. So, we just see now that what we have seen the magnitude. So, free metal ion, then somewhere in between we have the corresponding one where the overall energy is raised, and that overall energy raising is giving rise to the two sets of orbitals. The metal ion in an octahedral field gives rise to the delta O or delta 0 as the corresponding crystal field splitting. So, we want to measure the amount of splitting what we can have between these two levels, and the dz square and dx square minus y square point at the ligands and have higher energies than the other d electrons, and the energy gap which we will consider as delta is called the corresponding crystal field splitting. So, depending upon the geometry, if it is octahedral we will be labeled it as delta O, and if it is in tetrahedral geometry we will label it as delta T, and already we have seen that we have labeled this as the T2G set and the EG set. Thus, the corresponding available crystal field can split them into two sets. One is T2G and the other is EG. So, then next we will continue the other part, that means how we go for the corresponding values in a regular way. Thank you very much.